Hello and welcome in a new video. We will start with exercise 2.6. In this exercise, we'll use the normal and tangential acceleration to find the solution. A particle of mass m is launched from the point S0 with an elevation z0 equal r cosine theta 0 on a sphere with center O and radius r with an initial velocity v0. v0 is tangent to the sphere and is in the vertical plane passing through O. So we have a sphere here. On the sphere, we launched a mass m. It has as an initial position S0. So initially, the mass was at S0. The elevation of the mass at S0 is equal to Z0. So if we project the position vector R0 on the Z-axis, we will find Z0, where Z0 is equal to R cosine theta 0. So here theta 0 is the angle between OZ and the position vector R0. So we can predict that theta, the angle theta here, is counted from OZ. So theta is the angle between OZ and the position vector R. So for example, at the point S1, theta 1 is the angle between OZ and R1. So V0 is tangent to the sphere and it's in the vertical plane. So here the motion occurs in the vertical plane. It's the plane of the screen. The mass slides without friction on the sphere. So the mass initially was at S0. It slides without any friction until arriving to S0, to S1, where it leaves the sphere. So the mass started from S0. It slides without friction to S0. At S0, the mass leaves the sphere. Let G denote the acceleration due to gravity. We have 3 questions. Okay, so let's start with question A. Express the reaction R of the support on the particle as a function of its elevation z equal r cosine theta at any given moment and the parameters m, r, g, v0 and z0. So we need to find a force which is the reaction of the support. Let's find this force by applying the fundamental relation of dynamics on the mass m. So we need to find the reaction of the support, so the reaction of the surface of the sphere on the mass m. So let's draw the free body diagram. So at any point S on the surface of the sphere, we have as forces mg and r. We don't have any friction, so mg is always vertical downwards. The normal reaction R is always perpendicular to the support. It has this direction. Okay, so let's write the fundamental relation of dynamics. Sum of the forces equal ma, where F equal mg plus r. Okay, here, which acceleration will we use? In fact, in this exercise, we can see that we have like a part of a circular motion. And whenever we have a circular motion, it's very convenient to use the normal and tangential acceleration because they help us a lot in knowing the expression of the acceleration. So here, we wrote A as at plus an. So at is the tangential acceleration and an is the normal acceleration. To find r, we must project this equation on the direction of r. So let's draw the normal and the tangential unit vectors. The tangential unit vector tau is tangent to the path. It's directed oblique to the oblique downward to the right, as shown in the figure. And the normal unit vector is directed toward the center of curvature. It's perpendicular to tau. Okay, so to find the expression of r, we have to project the fundamental relation of dynamics along the normal unit vector, or along the direction of r. Here the direction of r is along n or minus n. Okay, so along n, we need to find the projection of mg along n. So it's mg, so we need to make the perpendicular of mg on the normal unit vector. It's equal to plus mg times cosine of this angle. And this angle is in fact equal to theta. So the projection of mg on the normal unit vector will give us plus mg cosine theta. And the projection of r on the normal unit vector will give us minus r. And this is equal to m(an) because we projected the acceleration on the normal unit vector. And we know the expression of an. An is equal to v squared over r. Okay, I didn't explain in fact why this angle is theta. So our point here is any point on the surface. It can be, for example, S1. At S1, if we draw the vertical line, and here it's mg, this vertical line has a direction of mg, we can notice that the angle between mg and the position vector is theta, because this angle should be equal to this angle, because these two angles are alternate internal angles. So this is the angle theta, which is this one on this figure. So we found this equation, and if we project the fundamental relation of dynamics along tau, we will find, so a projection of mg along tau will give us plus mg sine theta. The projection of r along tau is 0 because r and tau are perpendicular to each other, and the projection of a on tau will give us at. So we obtain two equations by projecting the fundamental relation of dynamics on the normal unit vector and on the tangential unit vector tau. Now the question is to find r, in fact. But we don't know what is v. What is v in this case? So we need to find v. From where do we find v? We have to use, in fact, the second equation to find v, where at is equal to dv over dt. So if we stop a few seconds on this equation, so mg sine theta is equal to mat, we can notice that the acceleration, the tangential acceleration, is equal to, is it equal to a constant? Or is it changing with some parameter? It's equal to g sine theta. G is a constant and theta is changing. So this means that the tangential acceleration is a function of theta. And if the tangential acceleration is a function of theta, then it's very convenient to use the relation v dv equal at ds to solve this exercise. Okay, so whenever we see that the acceleration depends on x or on theta, the angle of rotation theta, we can use this equation and it will give us a quick answer. We can write that AT is equal to G sine theta, so AT is equal to G sine theta, and we can write ds as RD theta, because ds is an arc, and the arc is equal to the radius, which is small r, times d theta. So based on this equation, can we find v? Can we directly integrate? So are the variables separated, well separated? So here we have v dv, and after the equal we have g sine theta rg theta. G is a constant, r is a constant, it's the radius of the circle. So here all the terms containing theta are apart, and all the terms containing v are apart. So now we can integrate. So the integral of v dv between v0 and v is equal to integral of gr sine theta d theta, where theta goes from theta 0 to theta. We want to deduce, in fact, the expression of v as a function of theta. So the first quantity will give us half v squared minus v0 squared equal, so gr are constant, they can come out of the integral. Now the integral of sine theta d theta is equal to minus cosine theta, and theta goes from theta 0 to theta. So this quantity will give us equal minus gr parenthesis cosine theta minus cosine theta 0. So please notice here that theta 0 is different than 0, because at theta 0 the particle was at S0. With this angle theta 0, it wasn't on the z-axis. The particle was here on S0, so the position vector is making an angle theta 0 with OZ. So please here don't forget this term, minus cosine theta 0. So the objective, I repeat, is to find the expression of v or v squared as a function of theta. We are more interested, in fact, in finding the v squared instead of v, because the relation of the expression of r, we have m times g cosine theta minus v squared over r. So we need to have v squared. So we can deduce v squared from this expression and replace it here in the expression of r to find what is r. But before, let's replace cosine theta with z over r and cosine theta 0 with z 0 over r, because in the question they told us to find r as a function of z0. So we need to make z0 showing. So we need to show the term z0. Okay, finally, we can write that the normal reaction is equal to m. So parenthesis g cosine theta is equal to g z over r minus v squared over r. So v squared over r will give us all this quantity. So again, I replaced cosine theta with z over r and cosine theta 0 with z0 over r. So here we showed z over r and z0 over r. Therefore, by adjusting the form of r, we can finally obtain r equal 3mgz over r minus 2mgz0 over r minus mv0 squared over r. And this is the expression of the reaction of the support on the particle as a function of z as a function of m, r, g, v0, and z0. And finally, r is equal to m over r, parenthesis 3gz minus 2gz0 minus v0 squared. So we answered part A. Now part B. Show that if v0 is greater than capital V, so show that if the initial speed is greater than a certain v, than a critical v, the particle leaves the sphere right from the start at s0. Determine v. So in fact, they are telling us that if v0, if the initial speed is high enough from the beginning, the particle will take off at s0. So if the initial speed is very, very high, the particle would leave the surface from the beginning at s0. So it will not slide on the surface of the sphere. So let's determine what is capital V. So the capital V, in fact, is the critical speed to be found. So in this question, how should we think? Let's express differently this sentence. The particle leaves the sphere. When does the particle leave the sphere, and when does the particle remain on the sphere? So the particle remains in contact with the sphere when R is positive, when the normal reaction is positive. So the inverse or the opposite of this statement is the particle isn't in contact with the surface, so the particle escapes from the surface or leaves the surface if R is smaller than or equal to 0. So the opposite of R is greater than 0 is R is smaller or equal to 0. So what is R here at point S0? So R at point S0 is equal to M over R 3gz minus 2gz0 minus v0 squared, where we have to replace z with z0, and then we can obtain that r0 is equal to m over r, parenthesis gz0 minus v0 squared. Okay, so this means that we replaced z with z0, then we have two terms containing gz0. 3gz0 minus 2gz0 gives 1gz0. Okay, this is this term. Our expression of R will become, so R is smaller than or equal to 0 at point S0. This means that R0 is smaller than or equal to 0, where R0 is this expression. It's equal to m over r gz0 minus v0 squared. So this will give us that gz0 minus v0 squared is smaller or equal to 0. And finally, we can find that gz0 is smaller than or equal to v0 squared. So we obtain that v0 squared is larger than or equal to gz0. This means that if we make the radical of this expression, v0 is larger than or equal to radical of gz0. So this was in the question. In the questions, they told us to find v, where v0 is greater than v. So we found that v0 is greater than or equal to this quantity. So this quantity should be equal to v. And finally, we can find the numerical value of V. So the numerical value of V is radical of GZ0 is equal to 3 meters per second. So the lower limit of V0 is V equal 3 meters per second. This means that if the initial speed at S0 is larger than or equal to 3 meters per second, the particle will leave the surface from the beginning at S0. So the particle will not slide on the surface of the sphere if V0 is larger than or equal to 3 meters per second. So why did I write this the equal sign? Because in fact, if V0 is equal to radical of GZ0, if V is equal to 3 meters per second, then we will have R equals 0, and R equals 0 means that we will not have any contact. So this means that the particle will leave the sphere at S0. Okay. Now question C. Calculate the path traveled by the particle on the sphere if it's released at S0 with a velocity V0 equal V over 2. So we need to find the path traveled by the particle on the sphere. So the path traveled by the particle on the sphere is equal to S to the arc S0, S1. We need to find S0, S1, the arc, the length of the arc S0, S1, if the particle is released at S0 with a velocity V0 equal V over 2, where this V is the same as this V. And we have already found that this V is equal to 3 meters per second. So we need to find the arc, the length of the arc S0, S1, if V0 is equal to 3 over 2, which means that V0 is equal to 1.5 meters per second. Arc S0, S1 is equal to R theta 1 minus theta 0, because in fact we already know that ds is equal to r d theta, where ds is a very small arc. It's a very small arc. Here we have the arc S0, S1. It can be written as R theta 1 minus theta 0. Do we know what is theta 1? Let's find. So theta 1. At R1, so the particle is at S1. The position vector makes an angle theta 1 with OZ. At S1, the particle leaves the sphere. So if the particle leaves the sphere at S1, this means that R is equal to 0, or R can be less than or equal to 0. Okay, but here we have to find the numerical values. We have to find what is arc S0, S1 equal to. Then we will write the equal sign here. Okay. So we want, the objective now is to find theta 1. So theta 1 corresponds to the position of the mass at S1. And at S1, since the particle leaves the sphere, so R is equal to 0. This will give us that R is equal to 3 mgz1 over R minus 2 mg0 over R minus, so here we have minus m over R v0 squared, where v0 squared is equal to v over 2 squared, and we already know what is v, so v is radical of gz0. So if you substitute here v0 with radical of gz0 over 2, you will find this expression for R, and this is R at S1. This should be equal to 0. Therefore, we can find z1 as a function of z0. So we will find that z1 is equal to 3 times z0 over 4, where z1 is equal to r cosine theta 1. Therefore, we can find what is theta 1 as a function of z0. So theta 1 is equal to cosine minus 1 of 3z0 over 4 r. So this is theta 1. We can replace theta 1 in this expression. So finally we can find the distance traveled on the surface of the sphere. It's equal to the arc S0, S1. It's equal to r theta 1 minus theta 0, where theta 1 is equal to this expression. And theta 0 is equal to cosine minus 1 of z0 over r, because z0 is equal to r cosine theta 0. So if we want to summarize this exercise, we can see that we applied the fundamental relation of dynamics, or the Newton's second law, on the mass m. We used the normal and tangential acceleration because we know that this is a part of a circle. So an and at are very convenient to be used here. Also, one important note is that the tangential acceleration is a function of theta. Therefore, we used the expression v dv equal a t ds. And one other important idea in this exercise is that if we have a contact with a support or with a surface, r should be positive. So the opposite of this statement is that the particle isn't anymore on this surface, so we don't have anymore this contact if r is less than or equal to 0. If you enjoyed this video, don't forget to subscribe to my channel.